Welcome back, all of you. In the previous video, we looked at the position time graph and learned how to extract a lot of useful information about the motion from that graph. Now we're going to look at a different graph of motion, the velocity time graph. We're first going to take the same position time graph that we worked with last time and generate a corresponding velocity time graph for it. And once we do that, we're going to summarize some of the key points about how to extract information about motion from a velocity time graph. So here's the position time graph we worked with last time. We had time on the x-axis in seconds, and we had position north of the origin in the y-axis in meters. And we divided the motion into 4 segments, and the endpoints were A and B for segment 1, BC for segment 2, CD for segment 3, and DE for segment 4. We also figured out the velocities for the various segments. For V1, you'll remember that our velocity was plus 1.5 meters per second, and it's a good idea for you to pause the video now and calculate that for yourself if you want. For segment 2, the velocity V2 was simply 0 meters per second. The object was at rest for that duration of 2 seconds at this position of 6 meters. For segment 3, the velocity V3 was minus 2.0 meters per second. Negative implied that it was moving in the southern direction, while in segment 1 it was moving in the northern direction, and in segment 2 it was not moving at all. And lastly, in the fourth segment, we had a varying velocity. We calculated an average velocity, but really what happened here was the velocity at point D was at minus 2 meters per second, and by the time it got to point E, you'll see that the curve is pretty flat, hitting the x-axis, and flat means the object has come to a rest. So this velocity changed from minus 2 meters per second to 0 meters per second during this duration. So I'll just show that as Vd is minus 2.0 meters per second, and Ve is 0 meters per second. So in order to generate the corresponding velocity time graph, I'm going to first shrink this graph and move it to the side to create some room. And set up a grid for my velocity time graph. So here's the grid for my velocity time graph. The x-axis looks the same as before. I've got time in seconds going from 0 to 10 seconds in increments of 2 seconds. But the y-axis looks very different because what's plotted now on the y-axis is velocity, not position as before. So I've got velocities both positive and negative because I know that I'm going to have velocities that are positive and negative. So I've got my grid set up correspondingly. And I've chosen to set up the grid increments as half a meter per second in the positive direction and in the negative direction because that seems appropriate for the data I have to plot. So now let's start developing this graph. So for the first segment, from 0 to 4 seconds, I had a constant velocity of positive 1.5 meters. So that looks on the graph like this, a flat line at 1.5 meters per second. Second, I had the object at rest from 4 to 6 seconds, which means its velocity was 0 meters per second. 0 for velocity lies right here along the x-axis, so my second segment would look like this. So the velocity right at this 4-second mark, the velocity changed from positive 1.5 meters per second to 0. The object came abruptly to a rest in this idealized example. And when that happens, we show that generally with a dotted line connection. So let me go ahead and do that here. For the third segment, I had a velocity of minus 2.0 meters per second. So minus 2 for velocity lies below the x-axis over here. So I go from 6 seconds to 8 seconds and have a velocity that's constant at minus 2 meters per second, like so. And then for the very last segment, we had the velocity changing from minus 2 meters per second to 0. So at D, which is at 8 seconds, the velocity was at minus 2 meters per second. And at E, which was at 10 seconds, the velocity became 0. So the velocity graph will look like this. It's no longer a constant. The velocity is changing with time. And let me go back and fill in this dotted line connection here for this instantaneous change of velocity. So that's our velocity time graph corresponding to position time graph. And right away you should be struck with one of our key points about graphs. Graphs are not a visual representation of a motion. They require interpretation to figure out what's going on. So we have two graphs here, both representing the exact same motion, but they look extremely different. And that's because in one of them we had position plotted on the y-axis, and in the other one we have velocity plotted on the y-axis. So now it's time to capture some summary points on how to read velocity time graphs. First, we have seen that for the first three segments, a velocity graph is a flat line, a horizontal straight line. And whenever you have that, that means the velocity is a constant, or that means that you have uniform motion. So our first point is that flat or horizontal lines in a velocity time graph are simply representation of uniform motion. Second, points above the x-axis have positive velocity, and that tell us that the motion is in the positive direction. What positive means depends on our coordinate axes. In this case, that means motion in the northern direction. But in a velocity time graph, any point that lies above the x-axis identifies motion in the positive direction, as in segment 1, and points below the x-axis, as here in segment 3, represent motion in the negative direction, as well as segment 4 represents motion in the negative direction. So that's our next two summary points here. And then points along the x-axis, which are neither above or below it, simply show the object at rest. The velocity is 0 for these points. So we got that summary point over here. And then we also discussed the fact that the object was fastest in segment 3. Even though it was a negative velocity value, the speed was the fastest here, because speed does not care about the sign. We had 2 meters per second speed here compared to 1.5 meters per second here. So in a velocity time graph, the distance from the x-axis identifies the speed. And since that's the largest for segment 3 is when this object was moving the fastest. Our final point tells us how to get displacement of motion from a velocity time graph, which is a way of tying back to the position time graph. So let's see how that works. The area under the curve or under the plot in a velocity time graph is nothing but the displacement of motion. So for our segment 1, the area under the curve is this rectangle that I'm shading in. And so if I want to get the displacement for this first segment, delta x1, that's just that area under the curve, which is, in this case, since it's a rectangle, it's the height times the width. The height is plus 1.5 meters per second. The width is 4 seconds. And so the seconds cancel, and we end up with plus 6.0 meters. And that's what we had before. The object went from 0, the origin, to a point that was 6 meters north of the origin. So its displacement was plus 6 because it was 6 meters in the northern direction. For the second segment, there was no displacement. The object was at rest. And here, there is no area under the curve. The plot is on the x-axis. So then that gives us an area of 0, which corresponds to the displacement during segment 2. For segment 3, we got another rectangle. So here's the rectangle that we need to figure out the area for. And because this area is below the x-axis, this would be a negative area. So delta x3 for the third segment is the area of this rectangle. The height is minus 2.0 meters per second. The width is 2 seconds, from 6 to 8 seconds. So once again, the seconds cancel, and I get minus 4.0 meters, which corresponds to a displacement from 6 meters to 2 meters. Remember, displacement was final position minus initial position, and as we saw before, 2 minus 6 is minus 4. And what that tells us is that this object is moving in the negative direction, which in this case is in the southern direction by 4 meters, back towards the origin. And then in our last segment, we don't have a rectangle anymore, we have a triangle. So here's the area that I need to figure out to get the displacement of this last segment. And so delta x4 would be the area of this triangle, which, as you know, is 1/2 base times height. So I got 1/2 times base, which is 8 to 10, which is 2 seconds. times height, which in this case is minus 2.0 meters per second again. Once again, the seconds cancel, one of these 2's cancel, and I get an answer of minus 2.0 meters, which corresponded to the very last segment going from 2 meters north of the origin to the origin was a movement of 2 meters in the southern direction, which we get from here. So that's a nice way to tie in and get displacement information from velocity time graph, and that was our final summary point for the velocity time graph. So in this slice of physics, we learned how to generate a velocity time graph from a position time graph, and then we also learned, if we are presented with a velocity time graph, on how to extract useful information about the motion from that graph. Thank you.